Hey everyone, welcome back. In this lesson we're going to continue talking about logarithms, which is the topic that we started last time out. We talked about a couple of properties of logarithms towards the end of the last lesson, which we will go over again. Let me just remember what we covered and what we didn't. Oh yes, so one of the things that we talked about is that if you've got something like log base a of some number a, where those two a's are the same number, then that'll always equal 1, because what it's asking you is what exponent do I have to raise this base a to get an answer of a. And we already know from when we were dealing with exponents earlier on that any number to the exponent 1 is just that same number back again. So that answer will always be 1. And the other property that we saw last time out was that if you have logarithm base a, so any number with an argument of 1 inside, then that means what you're asking here is what do I have to raise any number a to, what exponent do I have to raise any number a to get to an answer of 1. And so that answer there is 0. A to the exponent 0 is going to equal 1 no matter what this a is. So if it wasn't true for all the numbers, then we wouldn't be able to put an a here like that. So those are two properties that we saw of logarithms last time, is that answer there would be 0, so log base anything of 1 is going to equal 0, and log base anything of itself is going to equal 1. So those are the things that we saw last time out. And this time what we'll do is we'll start with just a little bit of a refresher on what logarithms are and how they work, which maybe I guess I should have started with, but we'll do a couple of examples to sort of remind ourselves of what logarithms are and how they work, and then I'll show you a couple more properties of logarithms. Now the properties that we're going to talk about this time, they're not the most useful if you're just working with numbers. They're more useful if you're working with a whole bunch of variables. So like if you were working with a logarithm where your argument is full of like x's and y's and letters representing quantities that you haven't found yet, letters basically representing unknown numbers, then these properties tend to be useful if you need to rearrange those letters in some special way. When it comes to working with just working with numbers, they're not as useful, but I'll show you them anyway, and then we'll stick to examples that use numbers, and then perhaps later on in the term we'll go back and revisit some of these things once we've done a little bit more with variables. So before we get to any of that, let's just go over a couple more examples of logarithms. So one of the ones that maybe I did, maybe I didn't do, I don't think I did this one, but there's a chance that I did. At any rate, we'll go through it. So just to remind ourselves of how they work, so let's say we wanted to calculate log base 3 of 81. So what we're trying to find here is what exponent do I need to raise this 3 to such that I get an answer of 81. Right? That's basically what this question is asking. And if you plug this into your calculator, you might see a box. There's an option to put exponents into your calculator. And so if your calculator is capable of that, depending on the display, you might see a box like that. And you plug in the 3, and then you push a button, and it goes up there and gives you that box. So I'm going to stop with the question marks just because I don't really like using the question marks. So I'll use boxes. Maybe at some point I'll switch over to letters. But basically, it's the same idea as what we were talking about before. So it's 3 raised to some exponent is going to equal 81. And the way we can figure out what that exponent should be is we'll just multiply a whole bunch of 3's together and see what our answer is. Now we know 3 times 3 is 9, so having just 2 3's being multiplied together is not going to be enough to get us the answer that we're looking for. So if we throw in another 3, then that'll be 3 times 3 times 3. This part here is 9, so it'll be 9 times 3, which is 27, which is still not enough. So we're going to add in another 3 there. I say add in, but I mean we're going to multiply another 3 into that. And so we've got 3 times 3 over here, that's 9. We've got 3 times 3 over there, that's 9. Those are being multiplied together. 9 times 9 is 81. So now we've found our target number there. We've got that 81, which tells us that we have enough 3's that if we multiply them all together, we'll get 81 as an answer. So we just count how many 3's we have. It's 1, 2, 3, 4. That means that it's 3 to the exponent 4 will give us an answer of 81, and therefore that means that the answer to our logarithm up here is going to be 4, because it's 3 to the exponent 4 equals 81. That's sort of the structure of the logarithm. Now, there's one other thing with logarithms that I didn't mention last time, at least I don't think I mentioned it last time. This isn't like a property of logarithms or anything like that, but this is more of a notation thing, which I might do on occasion. Your calculator probably does it this way as well. Some calculators do, some calculators don't, so it really depends on what you've got. And depending on the calculator, you might not even have logarithms on it. But if your calculator has logarithms, some of them have different ways of representing them. And the one that I want to draw your attention to is log base 10 of, I don't really care, let's put 100 in there. So, just for the sake of making it an actual question. So log base 10 of 100, let's go ahead and calculate that, and then I'll come back to the point that I was trying to make. So, what we want to find here is what exponent do I need to raise 10 to get an answer of 100? That's the question. And so, we just start off by multiplying some 10's together and see what that gives us. So first off, we'll start with a couple of 10's. So we'll do 10 times 10, and that equals 100. So right off the bat, we've got our answer for this one. And so that means that because we multiplied two 10's together, that our exponent here is going to be a 2. So it'll be 10 squared equals 100. And so that tells us that our answer to our logarithm is 2. Whatever that exponent down there is our answer up here in the logarithm question. Now the thing that I wanted to get at is that you could also write this as log 100. You might notice that there's something missing from that, and that's the thing that I wanted to highlight, which is that if you've got a logarithm with a base of 10, that is, it's going to be 10 raised to some exponent to give you your target answer, you don't need to write in the 10. And a lot of people tend not to write in the 10 down there as the little subscript. So basically, log base 10 of, I don't really care what the argument is, let's call it a for any or a for argument, is equal to log of a. You don't need to write down the little base, the little 10 down there, if it's 10. If it's any other number, you should put it down there. There is, some people will disagree with me depending on where they grew up or, what they've learned, the level of math that they tend to work with. Log a without any base can mean a different thing, but for our purposes, this is the common one for most people is that if there's no base written there, it means that there's actually a little 10 hiding in there. For some people it means something slightly different, but we're not going to worry about that because we haven't talked about sort of the significance of the other case. And basically, suffice it to say that there's another number that some people consider to be sort of central to their calculations, so they tried to use the shorthand for that number instead of for 10, but that's a number that we haven't really studied in detail. It's not pi, but it's similar in that it's another irrational number and it's a famous number and all of that, and it's got a special name, but we haven't really talked about that number or its value or why it's important, so don't worry about that right now. But I just wanted to point out that most of the time, when like 99 times out of 100, if you see this, without any base written there, it means that there's a 10 in there. So if I ever leave it out, I probably mean a 10 there, or I forgot. And based on the question, you'll probably be able to tell. So those are a couple of things that I wanted to go over before we get to some actual rules involving logarithms, which I will get to now. So we'll call this Logarithms Practice Problems in case you're looking for a title. My apologies for not really putting this up before, but Logarithms Practice or Practice Problems, your call. But yeah, so let me introduce you to the two rules. I'll write down both rules first, and then you can get them on your page, and then we'll refer back to those when we're actually going through a couple of examples. So the rules are as follows. So the first one is, if you've got logarithm base a, any base, I don't really care what it is, of, and then your argument is made up of two things being multiplied together. So let's call the first one m, and let's call the second one n. Alright, so we've got log base a of m times n. So this could be any two things that are being multiplied together. You know, maybe you'd be working on a problem. If you've got a thing with a lot of variables, then your variables might be the two things that are multiplied together. You might call them x and y or something like that. But you can see that right off the bat, if we're dealing with just numbers, why would we ever think to write a logarithm as something times something? You might as well just write the entire number in there. So it's not necessarily going to be useful for us, but it's a useful property of logarithms that you should at least see before you run into a problem where you actually need them. So what this is equal to, and this is sort of a neat trick with logarithms, is that log base a of m times n, so two different things being multiplied together, is the same as logarithm base a of m, just m, plus logarithm base a of n. Alright, so that's a bit of a neat trick with these two different terms being multiplied together within that argument, within those brackets there. This is a property of logarithms that you can actually make use of, depending on the question, of course. It won't prove to be very useful to us, but this is the way it works. So the logarithm base a of whatever that first term is, plus logarithm base a of whatever that second term is. Note that this base down here needs to be the same for all of them. So sometimes you'll be taking this and you'll be expanding it out to work with those terms, but sometimes you might have logarithm base a of something plus logarithm base a of something else, and you can combine them to make one giant logarithm instead. So you could have like logarithm base 2 of 4 and logarithm base 2 of 64, and you could combine them together and take the 4 from here, the 64 from there, multiply them together and put them in these brackets here as one big number. And then you just have one logarithm to work with from there. So that's the first rule. And the second one is very similar. So it's logarithm base a, again we don't care what the base is, and this time it'll be m divided by n, or m over n if you wanted to write it as a fraction. So m divided by n in the argument, you can probably guess where this is going. If the first one was multiplicative inside, that is, if we're multiplying inside, we're adding outside, we've flipped the operation here. Instead of doing multiplication, we're doing division. So it's log base a of m over n. So you can probably guess where this is going now. I'm hinting to it. it's going to be log base a of m minus log base a of n. Alright? So those are two useful properties of logarithms, and I'm actually going to use these, I'm going to use both of these properties to actually show you one more. Actually, to show you one new one, which we're not necessarily going to use very much, and also one of the ones that we've already talked about. So right now what we've got here is m and n, m and n. So this is the fact that we're using different letters, is sort of, it's got this underlying meaning that m and n are supposed to be different, or at least they're allowed to be different, and this thing is still true. If they had to be the same thing, then we can't write different letters for them. It would have to be m, 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 m everywhere. It would have to be just m's or just n's, or you could use another letter. You could use b, put b everywhere, if they had to be the same. But because they're allowed to be different, we'll put two different letters. But if they're the same thing, then that means we would have something like log base a of m times m, right? Which is the same thing as, well, the first term is m, so I'm going to have, this thing is going to be the same, so it'll be log base a of m, no problems there, plus, and then here's the thing, all I've done now is I've changed that n into another m, so that means I'm going to have a second term that's log base a of m. So these two terms are actually identical, right? It's making use of this property down here, but I've put two m's here instead of an m and an n. So I've got m, that term is identical, but here instead of an n, I have another m. And so we could simplify this down. This is one giant thing. It looks a little bit ugly. It's log base a of m, but this thing here and this thing here are identical. Agreed? We've got a logarithm in both of them, sure. We've got base a in both of them, sure. We've got an argument m in both of them. They're identical. So if you've got two identical things being added together, that's the same as just one of those things times 2, right? If you've got 4 and 4 added together, that's the same as 4 times 2. This is repeated addition is multiplication. So I could rewrite this as 2 times, I'll put the big brackets here just so that you can see everything's together, log base a of m. And so this thing here, this is all being multiplied together. 2 times this whole thing is all being multiplied together. And that's come from the fact that we've got log base a of m up here and log base a of m over there. So regardless of what that statement actually means, if we don't care what a is, we don't care what m is, as long as a is the same here and here, and m is the same here and here, those two terms will be identical, and that's the same thing as just having one of those terms times 2, right? One marker plus another marker is just a marker times 2. The number of markers that you have times 2, right? You know, like I was saying before, 4 plus 4 is the same as 4 times 2. 8 plus 8 is the same as 8 times 2. Log of m plus log of m is the same as log of m times 2, which is what we've written down here. But if you notice, we can rewrite this in a slightly different way. This left-hand side we can rewrite slightly differently, because this is m times m. Now we know from when we were dealing with exponents before that that's the same thing as writing, I'm going to have to squeeze this in here, that's the same thing as writing log base a of m squared. Do you agree? That's the same thing. If we had 2 times 2, that's the same as 2 squared. If we had 10 times 10, that's the same as 10 squared. M times m is going to be m squared. So, let me get rid of the rules line and the original rule that we took this from. And we can actually develop a new rule, a new logarithm rule, from what we started with. So we started with the one that I just erased, but now what we've got is, if you look at this, we've got log, I'm going to write this a little bit larger so that you can see it clearly. Log base a of m squared is equal to 2 times log base a of m. Right? Now, here's the thing. Here's the neat thing about it, is that we've got a 2 here, we've got a 2 there. That's not a coincidence. If this was a 3, that would also be a 3. If this was a 5, that would also be a 5. The thing with the logarithm rule that we were doing with this log base a of m times n being inside, it could be one term times another one times another one times another one times another one, and that's the same thing as logarithm of the first term plus the logarithm of the second one plus the logarithm of the third one plus the logarithm of the fourth one. So it's not limited to just 2 terms. In the example that we were doing, it was limited to 2 terms with the way I was writing out the rule, but it's not restricted to just 2 terms. So what we've got out of this is that if you've got an exponent of 2 here, you have a 2 out front. But you can try and write this out yourself and see if you can work out how this makes sense, or look it up and see if you can figure that out as well. If we had a 3 up here, we would have a 3 over there. If we had a 10 up here, we'd have a 10 over there. So we can actually rewrite this rule. Let me change that 2, because it doesn't have to be a 2, because it can be any exponent. Let me use p. I use p for my name. If we've got a p up there, we're going to have a p out here. And so this is a whole nother type of logarithm rule, just another property of logarithms, which is that if your argument has an exponent inside of it, you can take that exponent and pull it right out to the front. Right? I'm going to get rid of this stuff at the top now because we've sort of gotten our way to the answer. We can take that exponent and pull it right out into the front of that equation. Like we started with log base a of m to some exponent p, and what we've effectively done is we've just taken that p from over there, we've chucked it out here, and then removed it from up top. That's all that we've done. But that's a perfectly valid thing to do with logarithms. So that's just a neat property that you can get of logarithms. This is also a logarithm rule that people will use a lot. But the neat thing with this is that we took a logarithm rule that I gave you, and we have come up with, we've constructed, we've derived a new logarithm rule from that one. So sometimes you take a rule that you know, and then you play around with it a little bit, and it actually gives you another rule to work with. So that's a neat thing that you can do with a lot of mathematical ideas and a lot of mathematical proofs, is that you start with one idea, you fiddle around with the numbers, or in this case the letters, a little bit, and it spits out something meaningful as an answer. And so this is a property of logarithms that you can use anywhere, anytime, as long as you know, following the constraints that we've sort of put into place. That your all of the things inside here must be the same number, because otherwise you can't do this exponent thing. And if you've got like with this rule down here and the rule that we started with, they all have to have the same base. All of those things, if those things are in place and you've got an equation or you've got a term that looks like this, you're allowed to turn it into that if that happens to be more meaningful for the question that you're working on. Now, one other thing I wanted to show you is a similar idea, but with this rule down here. And so what we'll do this time is we'll replace the n's with m's. So I'll write this as log base a of m over m, which is the same thing as, if we follow the right side, well, that first side isn't going to change at all. It's going to still be log base a of m minus, now we're not going to have an n over there this time because we've changed the n that was our denominator here into an m. So we're going to put log base a of m again, right? And so what this has done for us is we've changed the n that was down here, we've changed it to an m right there, and the n that was over there, this n right here, has changed into an m up there, right? So right now that's not particularly meaningful, but if we simplify this one step down, we get, for this left-hand side, it's going to be log base a, m divided by m, doesn't matter what m is as long as it's not 0, m divided by itself, any number divided by itself is going to give us 1. Agreed? And if we look at the right side, we've got this giant thing, log base a of m, minus log base a of m. These two terms are identical. If I subtract one of them from the other, I'm going to be left with 0. Right? I've got this gigantic mess over here minus this gigantic mess over here. Doesn't matter how complicated they are, if they're identical and I'm subtracting one from the other, I'm going to be left with 0. And so this gives us back one of the properties that I sort of told you to just assume was real, or assume was true. And we sort of saw it with a few examples, right? 3 to the exponent 0 is going to be 1. 10 to the exponent 0 is going to be 1. And so we sort of came up with this from the rules of exponents that I told you, that anything to the exponent 0 is going to equal 1. But now we've used this property of logarithms, which admittedly I sort of threw this property of logarithms at you out of nowhere. But once you had that property, we've just tweaked with it a little bit. We've just messed with it a tiny bit, and it's given us the property that we'd already uncovered last lesson. So those are just a couple of things I wanted to show you. Now we'll just do a couple of examples that actually involve some numbers. I understand this might be confusing because we're doing so much with letters all of a sudden this time. I promise it's not going to be this way just out of the blue without you guys getting a warning from me. I'm not going to expect you to remember these formulas with like the letters and stuff on a test like that. So what we'll do is we'll do a couple of examples just so you can sort of see that you can see how they work in action. So we'll do one for multiplication and one for division, and then we'll call it a day. So we'll start with a division one. So we'll do log base 2 of 64 over 16. Alright, now if we follow the division rule, it's going to be log base 2 of the first one minus log base 2 of the second one. So like log base 2 of the numerator minus log base 2 of the denominator is how we have to set this up. So it'll be log base 2 of 64 minus log base 2 of 16. That's how we have to set this up. Now, log base 2 of 64, that's asking us how many 2's do we need to multiply together to get to 64. And the other one is asking us how many 2's do we have to multiply together to get to 16. So let's start with the 64 one. So we've got 64 is equal to, well, let's see, 2 times 2, that's 4, times 2 is 8, times 2 is 16. Oh, well, that's easy. Well, that's nice and easy. Let's put down the 16 one. We know is 2 times 2 times 2 times 2. That's 16 right there. We're just not done with this first line yet, right? This is 2, 4, 8, 16. So that one's done. Now 64, that's 2, 4, 8, 16, times another 2 is going to be 32, times another 2 is going to be 64. So 64 is equal to 2 times 2 times 2 times 2 times 2 times 2. So that's 2 to the exponent 6. And for 16, that's 2 times 2 times 2 times 2, or 2 to the exponent 4. So since we've figured out now that 64 is 2 to the exponent 6, that means log base 2 of 64 is going to be that exponent there, which is 6. So we get a 6 for this first side. This whole left-hand side right here, this log of 64, is equal to 6 minus, and then log base 2 of 16, which we've figured out is going to be 4 because of that exponent over there. So it'll be 6 minus 4. I'm going to have to get rid of these lines now, unfortunately. So we're left with 6 from the first logarithm and 4 from the second logarithm, which is going to leave us with an answer of 2. Now the other way you could have solved this, and this is where using the logarithm rules isn't necessarily the best way to solve this problem, is we could have rewritten this as 64 divided by 16. We could just go ahead and calculate that. 64 divided by 16, if you want to do it with long division, you can, but 64 divided by 16 is equal to 4. You might have already noticed that, but if not, you could always calculate it with long division, and you'll get 64 divided by 16 is equal to 4. So I might as well just write a 4 in the brackets right from the get-go. Instead of leaving it as a fraction, I might as well solve that fraction, get it down to one number, and then I'll solve for that. And so if we've got logarithm base 2 of 4, that's asking what exponent do I have to stick on a base 2 to get an answer of 4. And that is going to be a 2, because we know 2 squared is equal to 4. So here we've got an answer of 2, and over there we have a 2 using the logarithm rules. So you can hopefully see that these rules do work. Alright, we'll do one more. And this time we'll do a multiplication one. So let me get rid of everything here. This is just so you can see that these rules do indeed work. And then next time out we'll do a little bit more with practice problems. I was getting a little bit too excited with going down a rabbit hole of those extra exponent rules, or logarithm rules. This time let's do log base 3 of 81 plus log base 3 of 9. So this time I'm using the logarithm rule in the opposite direction. I've started with 2 logarithms and we want to turn this into one logarithm. Log base 3 of something. Now, you have to make sure, before you can just throw them into one logarithm, you have to make sure that these 2 bases are the same. And if they are the same, then it'll be the same over there as well. If they're not the same, this rule does not apply. So you have to be careful about that. But now, let's go ahead and figure that out. The answer to this will be how many 3's we need to multiply to get to 81. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So it's going to be 4 3's multiplied together that give us 81. So my answer to this first term, this first logarithm, is going to be 4, because that's how many 3's I had to multiply together to get to 81. Now for the second one, it's how many 3's do I have to multiply together to get to 9. Now if we just go ahead and do that, we'll get 3 times 3 equals 9. We've only multiplied 2 3's together, so that means that my answer to that logarithm there is going to be a 2, right? So I'm going to have 4 plus 2, which is going to give me an answer of 6. But what we've actually done here is, because we've solved each of these logarithms independently, we haven't used the logarithm rule yet. We've just treated this logarithm as one thing and solved it by itself, and we've treated this logarithm as one thing and solved it by itself, which is not making use of the logarithm rules. If we wanted to use the logarithm rules, we have to approach this slightly differently. But let's keep that 6 in mind and see if we get the same answer, because this is the final answer to the problem, right? We dealt with the first logarithm, we got 4. We dealt with the second logarithm, we got 2. We added those together, we got 6. So we did get an answer, and let's just see if it was the right answer. Now to check that, instead of solving these 2 logarithms independently, what I'm going to do is we're going to make use of the logarithm rule that because these are being added together and we've got the same base, I can multiply the 2 things that are in the brackets together. So that is 81 times 9, which if you go ahead and do the math, that should give you 729. So that's what we throw in the brackets over there, 729. So now we've at least got it down to one logarithm, log base 3 of 729. Now admittedly, that's a tougher logarithm to solve because, well, we're dealing with larger numbers. Let's see if we can still get that 6 that we got the first way that we were solving it. So how many 3's, what this logarithm up here is asking us to find, is how many 3's does it take to multiply together to get to an answer of 729. So if we just start from the beginning, we get 3 times 3, that's 9. Times another 3, that's 27. times another 3, that's 81. We've got 81 so far. Times another 3, that'll be, what, 243? We've got 81 times 3. 3 times 1 is 3. 3 times 8 is 24. Yeah, so we're at 243 right now with this. 243 right there. Now if we multiply another 3 into that, we're going to have 243 from the first few times 3. So if we go ahead and calculate that, we get 243 times 3. 3 times 3 is 9. 3 times 4 is 12. 3 times 2 is 6, plus 1 is 7. And that's the 729. That was our target. So now that we've hit that target, we just need to count how many 3's did we multiply together, and that'll be our answer to that logarithm over there, log base 3 of 729. So if we count that out, if we count out how many 3's we used, well, let's do that. 1, 2, 3, 4, 5, 6. We multiplied 6 3's together. So that means our answer to this logarithm right here is just 6, which is the same answer that we got when we solved it the first way. So now you've seen two different questions using two different log rules going in opposite directions, and you've seen them solved in a couple of ways each that gave the same answer. So hopefully you have some faith that these logarithm rules actually do work. But yeah, so those are just a couple of interesting properties about logarithms. Again, they're not going to be the most useful if you're just dealing with numbers. It would be easier to perhaps solve these two individually, but if you only wanted to solve one logarithm, then that would be the way to do it. First, turn both of these into one, and then just solve that one by itself. But yeah, so in the next lesson we'll continue with some practice problems. Maybe we'll do a few more involving these logarithm rules. Perhaps we'll mess around with that rule with the exponent business, having that exponent in your argument and pulling it to the outside. Maybe we'll explore something like that in greater detail. But yeah, until then, hopefully all of this is making sense, and if you have any questions, get in touch with me. Otherwise, I will see you in the next video. Have a good one.